Okay, let's see. Okay, hello, I'm Piotr. Actually, I think I found my Rust job through Alex's site, I think. So yeah, kudos to him. And yeah, I'm also from Krakow, and I actually spent a few years in this area when I was studying at this university nearby. Maybe some of you studied on this technical university too. Good old times, that was like 15 years ago or something, but anyway. So today I'll be talking about message streaming, what it is, and how we could, let's say, build our own platform from the scratch in Rust if you've ever decided this for any reason. And actually, before I begin, when Wojtek and Rafał, whom I met at Rust meetup in Gliwice a few months ago, when I seen them doing this, let's say, Rust tour Poland, I had this flashback because I actually come from C#.NET. I spent like a decade in this technology. So we did something similar like 8 years ago when we traveled through the Poland, and there was this .NET Core, technology, cross-platform and stuff. So we did something similar. So kudos for them, because I know how difficult it is to travel through the country and just organize these meetups. So this is really cool. Now, so like I already mentioned, I come from .NET. Any one of you has done something in C# maybe, or Java similar?
My first job was in C#, and actually doing this in .NET Core. Even just at the moment it would release the first version.
Yes, it was fun times. Like everything was breaking after next release.
yeah, like everything was changed like almost every week.
Yeah, I think like since like version 3.0 it wasn't still. Yeah. So yeah, I come from .NET, and somewhere like a few years ago we started doing some open source. Started doing some YouTube videos, teaching people through some workshop companies and stuff like this. I got this MVP for this community activities in open source. But it was like 2 years ago, plus 2 years ago, when I just decided to try out something new, and I just picked up Rust at this time. I decided it's time for a change, as if having a newborn at home at this time wasn't challenging enough. I decided to do also this part. So currently I work at this Rust company. This is Huggin.io, cybersecurity startup, and I also recently joined the Apache Foundation. I'm one of the it's called PPMC, Project Polling Member Committee. So I'm like one of the persons managing the project here. And the story goes that so I've been doing this messaging. I mean, I use different kinds of messaging, whether it was like some low-level peer-to-peer, let's say, communication between nodes when I work at some Web3 company, or whether it was more about some generic purpose event-driven architectures or some financial system. So if it was Netty, ZeroMQ, RabbitMQ, Kafka, or Aaron. Have you ever, for example, used Aaron? It's quite popular in financial companies. It's like very highly performant message streaming, message streaming infrastructure. It's written in Java, but it's really like state of the art. So I use these different kinds of technologies. I assume you probably use maybe Kafka, Rabbit, or something like this, right? And I had this feeling that, okay, some of these tools are like easy to use. They have like very nice ecosystem, a lot of SDKs, but maybe they are not performant enough. While, for example, Aaron is like, it has great performance, great latency, but at the same time, let's say, there were just a few SDKs, and the overall complexity of setting this cluster up and all these things was really a bit overwhelming. So I just decided to, learn Rust, and I wanted to get my job in Rust, just because .NET, kind of bored me after 10 years or something. And I like to learn stuff by doing something more than just to do or stuff like this. Yeah, so I decided, okay, so yeah, let's just read some books about designing these data-intensive apps and databases and stuff like this. Let's pick up the language. And since I am the owner of 2 Italian Greyhounds, I just decided to go with this project called Iggy. And this talk won't be about this project itself. It will be more about all the experience that we've gained when we still implement this because it's grown quite a bit. And hopefully some of these experiences, if you work with us, you can maybe use some of the mentioned techniques or libraries or stuff like this in your daily program if you are, if you consider like high performance as something worth chasing, to put it that way. So yeah, it started 2 years ago, and over 2 years ago, and this year in February we managed to move this under Apache Foundation because we simply wanted to ensure the community that it remained like a free and open source project forever to use. So it's now part of the Apache incubator, and yeah, so we just keep keep working on it after hours. There's quite a good team of external contributors and like a core team and keep working on the project. So in general, if you ever use, for example, Kafka or something like this, yeah. What are your feelings about the tooling or SDKs?
Well, I mean, it's breaking all the time, like there is something like not working all the time, like something's always inconsistent, there are just million different configurations. It's like very hard to update and work with it, and actually SDKs for different languages is actually problematic, and there are issues all the time. It's not even telling about like issues about Kafka architecture itself, like if you join more consumers, one will just got disconnected, one got rebalancing, and the order of message you expect actually got broken. It's a different story, but I hate it.
I mean, that's quite common because when someone, let's say, from Java, ecosystem joins our Discord, I mean, typically Java developers are quite happy with Kafka because in Java, the SDK and all this tools in Java is like a first-class citizen. But in other languages, it's typically a wrapper on top of this already Kafka, and people don't like it that much. But yeah, coming back to Iggy, so it's like an alternative to Kafka, Redpanda, Aaron. We use our own protocol, so it's written in Rust, supporting different protocols like TCP, Quick, HTTP, maybe WebSockets in the future. We focus a lot on the performance, and we'll talk more about performance and all the techniques that we already did and we do and we plan to do in the future to make this as performant as possible, because performance is, both about high throughput and at the same time low and stable latency, because you don't want this, occasional spikes in latency when, let's say, every 100 requests goes to like 1 second in latency or things like that. But yeah, I mean, depending on the hardware, you can get like 5 or even 10 gigabytes per second. I mean, gigabytes, not gigabits per second, when it comes, for example, to like consuming the data. And yeah, we have a quite vibrant community. We work on SDK for different languages. We focus a lot on the benchmarking side, as you will see in a moment, which also helped us shape this talk and all these techniques, because we treat this as some kind of regression testing to see if the performance goes up or it stays at the same level, or if it goes down, hopefully not. And we also have like additional tooling like command line interface, our own connector runtime, like Kafka Connect, for example, where you can build your plugins in Rust to sync or pull or push data to different sources. We even recently released our model context protocol, so you can, for example, plug in your cloudy desktop or other MCP compatible tool and just talk to the server using your natural language to do something with the data, web UI, and stuff like this. So just a quick overview. Besides the server, there is a regular terminal. There is a web interface. There is like another CLI for the benchmark purposes only, different kinds of setup, message sizes, payloads, batches, these sort of things. This sort of platform, which is again part of the open source repo, where you can just browse different benchmarks, see how they change over time on a different hardware. There is the connectors runtime, and there is also like this MCP server. Here's an example of my cloudy desktop talking to this Iggy. Okay, so this is about the Iggy part. Now let's focus on the infrastructure. So what actually is the stream? And I found this, let's say, quote that the truth is the log, right? The database is a cache of a subset of the log. So, anyone who's ever worked in a database or read something about database internals, there is typically this concept of this write-ahead logging, where you just apply all these commands to have this persistency in case something goes wrong, and then you like kind of commit this and you write your data to the actual, let's say, tables, right? You have this sort of snapshot. But the truth is the log. So log is nothing more than just a collection of records appended to the top of this log. So pretty much this is the whole stream. You have a very simple data structure. You can think of it as some sort of a stack maybe. I mean, there is no like stack operations, but a stack in a sense that you apply on the top of the stack. So you apply the records or messages or elements, however you call this. It can represent any kind of data. You applied it to the very top. And you have this concept of like index that we typically call offset, starting from 0, of course. And this is how you can travel through this log of records, whatever these logs are. And this is immutable, of course, so you cannot modify the logs in these elements in the middle. You cannot delete them. I mean, of course, you could delete them. There are techniques to delete like part of this, let's say, maybe expired log or some part of log marked for the deletion. But in general, this is immutable, persistent data living somewhere in your disk or S3 storage or whatever you put it. And what this gives you in terms of writing or reading data from is that when you have like multiple clients, it can be any kind of application, they can just read this data in parallel, right? So let's say typically there is like message broker versus message streaming. So there's of course many like differences between these two different kinds of tooling. But one of the core differences is that in the message broker you have a queue. So you have first in, first out. If you want to have like 10 independent consumers, right, working in parallel, dealing with messages in their own pace, you need to like replicate this message across 10 unique queues. Because when you consume the message, it goes out of the queue, it's gone. So the other consumers like must have the same message in their own unique queue. With the stream, you have a single stream, it's immutable, you cannot delete data from it, it's persistent. So you just can have like hundreds or thousands of consumers just reading data from the stream at the same time. Of course, when you append data to the stream, you of course need to either lock it or you just read before appending. And that's obvious, but for the performance reasons, this is where it makes most sense. So when you think of throughputs like hundreds of thousands of millions or of messages per second, streaming is the way to go because it fits use cases, right? Real-time streaming, some kind of like high-frequency trading, this kind of companies, this kind of software. This is where it works best. Okay, so here is the great Linux. Now let's try to build something very basic, our hello world streaming infrastructure, and then we'll see where are all the complexities. Because looking at this simple diagram, I mean, when I told you that it's been 2 years and there is like, plus 50 contributors, maybe like around 5 or 10 contributors working on it on a daily basis, you could think that I'm crazy. Like, how can you spend 2 years building this, right? You just append data and read data, right? What the hell? Okay, so let's try to explain. So here is our hello world stream. So the stream will be a very simple structure. Identifier, because as you can imagine, we might have like multiple streams, right? Independent streams somewhere on disk. It will have the current offset. So let's say offset equal to 1,000 will mean that we'll have 1,000 plus one message because it starts from 0, and the path, like where it's stored on the disk. And of course, stream will have like 0 to n messages, and each message will have its own offset, 0, 1, and so on. And the payload, where the payload can be an arbitrary vector or collection of bytes. We don't care if you use JSON, protobuf, SBE, XML, doesn't matter. You just append random bytes and read random bytes, and we give it to you. So at this point, we need like 2 methods to interact with our stream. We need a way to append data, let's say message, record, data to our stream, and we call it polling. Because another difference when it comes to, let's say, message streaming and message broker, message queues, is that typically message queue work in a push mode. Whenever there's a message in the queue, they will push the data to the client. While with the streaming, you work in a polling mode. So it's like long polling, for example, with HTTP. It's on the client side to, has its own pace and poll as many messages as this client can consume. So anything related to like dealing with back pressure is on the client. If you can consume 1 million messages per second, it's fine. If you can consume only 1 message per second, it's really up to you how fast or how slow the polling is. So the polling is all about just returning this list of messages, starting from the specific offset, then taking, let's say, 10 messages from offset at 1 million value, for example. Okay, so next step is the serialization. So like I said, we will not enforce user to use any specific schema. It's same, for example, for Kafka, same for Rabbit. But in Aaron, they enforce you to use simple binary encoding. So you have to write your custom codecs, you have to describe your schema, because it works best for the performance reasons, because binary encoding is like 0 copy or close to 0 copy. So it's very fast, but of course, it's, let's say, not as pleasant to use. If you were to build like a regular event-driven microservices, it's a bit of like boilerplate code and codecs that you have to implement. So at this point, we don't care. You can just send out whatever you want. So when we want to, let's say, serialize the message, we have the offset is like, let's say, 64 bits, 8 bytes integer, unsigned integer, the payload length, and the actual payload of bytes. This is our whole message, serialized to bytes. And the other way around, when you want to read this message from the disk, we have the offset, first 8 bytes, we have the length of the payload, next 4 bytes, the payload itself, and this is how we read the message, right? So very simple serialization, deserialization when it comes to writing and reading data from the disk. Now, if you were to, let's say, do some hex dump or check how it looks like on the disk, this would be something like this. Maybe if you, let's say, include some identifiers, timestamp, metadata headers, there will be more data, but this is something extremely simple when it comes to the storage. Now, let's talk about the storage, because like I said, the stream is not only immutable, but of course, to be immutable, it has to be persisted somewhere, not just in memory. So it can work, it can be reloaded after the restart or a crash. So let's say you want to append the data, append the message to the disk. So at first, we increment the offset by 1. Of course, if this is the very first message, it will be set to offset 0. So there's like one more if at this point. So we take this message, we assign the offset, current offset to this message, serialize these bytes, open this file where the path is the path of the stream on the disk, write all to the disk. And we appended the message to the disk. Now the question is, like, durable file storage. At this point, it's not, because here we are not doing any kind of additional I/O synchronization, right? So it's like maybe not highly possible, but in theory, it's possible that when we call this write all, the data may be lost, right? Because it might be somewhere in the cache of the operating system, and before our operating system decides to asynchronously dump this data into the disk, there might be, someone might pull this switch or turn off the computer or whatever. These things happened, and they will be happening maybe once per year, maybe once per month, but we have to be prepared for this. So of course, the simplest reason would be to, let's say, call this syncall, flash, depending on the language. So in essence, just invoke this syscall of fsync, right? Syncing this data to the disk. However, the fsync has its limitations or has its performance hits. And this actually comes from, I think, Kafka documentation. And yeah, so they simply tell you that the frequency of this application level fsync, it will have like very large impact on your latency and throughput, because it can easily degrade your performance by like an order of magnitude. If you were to invoke this fsync syscall for every message, your throughput and latency will be very bad, to put it mildly. So there are like 2 workarounds for now, and we'll get back to the syscall and fsyncs later on, I promise you, and we'll see how we can deal with the fsync, or how we can actually get rid of the fsync at all and still have this durability in our infrastructure. So at this point, we can do these 2 things. Implement some sort of flash interval, or also implement some sort of batching. So one of the simplest, let's say, features or optimizations that the message streaming infrastructure does is just implementing the way of batching your messages. It also is also the same on the client side. So when you have an application, whether this is producer or a consumer, you don't typically send one message after another. You would rather batch them into maybe 10, 100,000 of messages and make a single network call instead of 1,000 separate network calls, right? Because it's just wasting your network I/O, and especially if you have an app which produces a lot of messages at a time, it makes much more sense to maybe send messages every 5 milliseconds in a batch of 1,000 messages than try to send them one by one. That would take 1 second or so. So at this point, we can assume that the client might decide to send us a batch of messages, and within our append, we can simply do the following. If we do not hit this specific threshold, let's say 1,000 messages, sorry, we don't do anything. But if within our internal in-memory buffer we have exceeded this threshold of unsaved messages, only then we serialize these messages as a whole batch, and then we dump them into the disk. We flash this data into the disk. So now this is great. This will greatly improve our performance, given that we decided to use fsync. However, as you can probably imagine, what if we don't hit these 1,000 messages for a long time? They'll be just waiting in memory, and someone might turn down the server. So this is why in this quote I showed you a few months ago, they also said, yeah, so batching and also some kind of flash interval. So to mitigate this risk, we can also introduce a very simple let's call it background saver, where every whatever we decided to be, 1 second, 10 milliseconds, 100 milliseconds, whatever, we might just have a simple job checking, okay, if there is any data in our cache in memory, in our unsaved messages buffer, if yes, just dump it to the disk, right? So we either save data when we reach this messages batch, this limit, or when this time has passed. However, as you can imagine, although this is fine, it's still not great because it's like still possible that we might not hit this limit of this buffered messages. We might not trigger this interval if this is happening every few seconds, for example, and we might still lose data in theory, right? So we'll get back to this, but at this point, let's say this is good enough for our scenario. Somewhere along the way, sooner or later, you would certainly like to have some sort of clustering because even if you were to f-sync every single message and even if the performance was still great, you still have to remember that your virtual machine might be gone for whatever the reason. Your disk might crash, and there's like maybe 1% or less that the data just is corrupted for whatever reason, for the hardware reasons or any other reason. So of course, at some point, you want to implement some sort of clustering. And of course, clustering is another story, but you want to have this to provide this high availability and reliability of your infrastructure. Whether this is database, queuing system, messaging system, anything, you typically want to have some sort of clustering in place. But like I said, this is like a story for another talk or series of talks. Anyone who's ever worked with clustering probably knows how wide and how complex this area can get. So just to have in mind that this is something that we would need to implement anyway. But let's get back to the fundamentals. So let's say we want to read this data. And we want to read the data starting from any offset. Let's say, sorry, we have like 1 billion of messages, a lot of messages, and we want to read data from offset 1 million. At this point, to read this message, I would have to pretty much traverse from the very beginning, load a lot of data into memory, and OK, there is my message at offset 1 million. Here it is. So what we can do is to implement like a very simple concept of indexing. So just like in database, or even simpler. So if I want to read the data starting at a specific offset, I can simply, next to my stream, my records, I can also have the additional file. Let's call this an index. And within this index file, for each record, let's say for offset 0, I will have the position of 0. That's obvious. And then for offset 1, I will save how many bytes I used to save the previous messages. So let's say the first message took 20 bytes as a whole. So I know that offset 1 starts from, let's say, position number 20 or 21. So for each of my message, I keep track of this offset, like how many bytes I used in total to get to this offset. And by doing so, whenever we append the data to our stream, we additionally write this offset, this index with the total bytes used before saving this message. And when we read this data, we simply open our index file and then just jump into the specific index. And OK, I need to, let's say, ignore 1 million bytes before to start from offset at 1 million or 100,000 or whatever it is. So very simple concept of indexing. But of course, keep in mind that now we have the elements, the messages, and then another file, which is index. And of course, in the index is gone. We can rebuild this easily. But we need to have this in order to speed up reads, because otherwise, this will be like very, very slow. OK, just give me a sec. I'm still not recovered yet. And here it will be a bit interesting, because now these were the basics. So somewhere along the way, we decide that, OK, we want to introduce networking, because we build this server for our distributed system. And even if it's a monolithic system, like a database, we need some network to talk to the system. So we'd expose, let's say, TCP, protocol, QUIC, UDP, whatever it is. We have a bunch of clients talking to our server. So at this point, our server could look like this. So we have a bunch of streams. Each stream has its own unique identifier. And we have a bunch of connected clients. Let's say each client has its own identifier, some client struct representing IP address, maybe some permissions, stuff like this. So from the server perspective, when we want to append the data, we then, let's say, provide the stream ID, message or a batch of messages, and then we simply do a lookup. Find the stream, do some locking, append that data. Same for polling. Stream ID, how many messages, starting from which offset, do the lookup of the stream, return the data. However, the things, of course, get a bit more complex, as with this model, we need to introduce some kind of synchronization mechanism. So the simplest way would be probably to just have some, arc, rwlock, or mutex, whatever, because, I mean, for reading data, we don't care. But when we write the data, sorry, as you can see here, when we write the data, we have to, at first, find the stream, and then, of course, log this, right? We cannot have the simultaneous writes from multiple clients, or this code, of course, wouldn't even compile if we didn't have this lock in the first place. So we need this locking. We need to log the stream when we append the message. And let's say for the polling, we don't need to log. We can have the read lock, so we can easily scale this to hundreds or thousands of consumers of the same stream. So for the reading, it's very efficient. For writing, of course, it's not that efficient because we cannot. I mean, we can only append the data one by one, one consumer after another. So let's say it will now look like this: some kind of arc RW lock for the stream, and we either do write lock or read lock depending on the use case. Now, when you talk about the streaming, there is typically this concept of topics and partitioning. So the idea is that that in order to, let's say, support some sort of concepts, let's say we have an e-commerce system or something like this, and we decided that we maybe collect the click events on our website or track orders or whatever. And instead of, let's say, appending this data to the single stream, because we might have a lot of producers or a lot of consumers, and we want these consumers, let's say, consume data at the same time. But at the same time, we don't want this consumer to, let's say, consume the same messages and have some duplicated tasks or jobs. So we can simply divide our stream into multiple independent streams that we would call partitions. So now what we call the partition is the same stream as we've talked already. But the idea is that we group these partitions or these streams together in this concept of topic, where the topic is just this logical grouping of things. So across these partitions, we might have the click events, but maybe these click events will come from different users, different order IDs, so they will be independent to each other. And by doing this, we can easily horizontally scale out the amount of data that we can produce at the same time and read at the same time by independent producers and consumer. So this is just a way of creating multiple streams and just saying, okay, so these 10 streams are actually related to each other, and we call them a group or topic of something, right? So this is pretty much the whole idea of partitioning. And let's say one of the usage of partitions is that, like I said, you might want to, let's say, enforce the ordering of, for example, specific messages which were originated by user with ID 1 to 3. We want these messages to be always at the partition 1. So we only care about, let's say, ordering per user ID or per order ID or per whatever. We want to enforce these messages, that these messages will be at the same partition. So we can do this by having such a simple, let's say, algorithm as partition ID is just the hash of some arbitrary key that we assign to our message or message batch. So we enforce this streaming server to always put the message with same user ID on the same partition. So when we consume them, we can be certain that this was the first event, second event, third event, that it wasn't spread across different partitions or different streams, and that things will be kept in order. So this, let's say, ordering guarantee will be always at the partition level. We can have this ordering guarantee from the server-side perspective across different partitions. So this is what it's all about scaling out and being able to produce and consume more data if there is a need to do this. So from our, let's say, server perspective, the only thing that changes is that now, instead of stream, we will just have a topic, and the topic will now have the partition. So the partition becomes our stream. It will have its own identifier. It will have its current message offset. It will have its path on a disk. And that's pretty much it. So the partition is our unit of work, is unit of this parallelization in terms of reading or writing data too. So this is our server. It will consist of topics. each topic will consist of partitions. And this is where we would do this locking, because we write to partition or read from partition. So this is like whole magic behind the streaming. And this is pretty much all there is if you were to build like a very simple message streaming. You can start with a stream concept, and then you can just, let's say, extend this stream concept to these topics and partitions, and that's pretty much it. So if you were to build your own database, there is much more work to do. With streaming, it's quite simple. But yeah, this is, of course, where things get a bit more interesting, as we'll now talk about the performance. Because, I mean, this will work fine, even if you use Tokyo, mutexes, all the like fundamental stuff, this will work fine. But from this level to the next level, where by next level, I mean like, I don't know, 5 or 10 times the performance, is like another, like bunch of things that you can implement to make it work as it should work, especially if you want to compete with the other tooling that is out there. Like there is Redpanda competing with Kafka and Confluent, right? There is Aaron, who is like pretty much the way to go for some of these financial and trading companies. So I would say there is quite a lot of tooling in this niche, but you could say the same about database, ecosystem or open telemetry ecosystem. There is like a lot of tooling, but there is still more and more tools showing up. They do think differently, and they somehow turn out to be better, more performant than the previous tooling. Okay, so when we talk about the performance, like I already mentioned, it's not just about the throughput. Of course, we would like to have our, let's say, streaming server to be able to, ingest 5 or 10 gigabytes of data per second. So we want this throughput to be very high. But at the same time, I would say that, yeah, the latency is equally or even more important. So especially for, let's say, exchanges or financial companies, you want this latency to be like sub-millisecond, for example. And you want this P99999 to be very stable. You don't want to see your every 100 message go to 100 milliseconds, right? Because it might kill your business. So once again, depending on the enterprise, it might differ, but both of these things are equally important. And so in order to achieve this, we have to utilize our CPU, our memory, and our I/O, right? Network I/O, disk I/O, storage I/O efficiently. Because the higher the efficiency, the lower the cost, right? So typically, the enterprise, wants to save money, right? If they can switch from database A to B, and they will have to spend 50% less money on the servers, that's a win for them. So for example, like recently, we've had one guy from Datadog joined our Discord, and he shared that I think they were running like 1,500, so 1,500 nodes to keep their Kafka clusters up and running. And I've seen recently an article on LinkedIn about Datadog's infrastructure and how they pretty much build their own version of Kafka to deal with all these complexities and edge cases to fit their scenarios. So this is like insane scale, right? And if you could let's say I can imagine they invested like a lot of money into this, but if you could tell them, I can cut down your cost by 50%, so at a scale like this, like at thousands of virtual machines that can, and network traffic, disk storage, that costs, I can imagine, like millions of dollars per month, probably to run it somewhere in the cloud, that's a huge win for a component like this. So it's like, you can see these things, especially when you're at the particular scale. Like when you have a single virtual machine, like for $100 and $50, that's something, but you don't care that much, right? But for stuff like this, it can be like very interesting use case. So one of the, let's say, maybe low-hanging fruits, but sort of the techniques, is what we would call this zero-copy deserialization. Have you ever heard of it, or maybe tried to use it, implement it? Have you heard about this?
Complex to implement. You need to pass lifetimes everywhere. And once you have async, you basically very often need to copy it because you need boxed feature with a static lifetime. But it's possible to do.
But have you tried to do this on your own, or have you used some library, maybe?
I've tried to do it on my own.
Did it work eventually, or?
Yeah, it's like not practice at the moment. It was like more something I wanted to do just to experiment.
Okay, so just to give you an overview of what the zero copy deserialization is, because it sometimes sounds like a bit of magic. In theory, it's it can be a bit difficult to implement, but again, depending on the use case. So for the streaming, it's not that difficult. For database, it might be more difficult. However, the whole idea is that whenever you work with the serialization, and I would say that I would assume that probably all of us here work with some sort of serialization at some point, whether expose some API, have some backend services that talk to each other, you need to send this data through the network and stuff, JSON, BSON, protobuf, whatever, right? So let's say when you receive this data on the server side within your consumer application or producer application, and let's say you receive the JSON, typically this regular serialization, let's say using SERDI JSON or library like this, it consists of these two stages. So at first, you have to you read this data, you read it somewhere in memory, then you parse it, and let's say you have a SERDI which can be supported by different schemas. So when you read it into memory, was like a first step, and parse it, then you decide, okay, so this was JSON, this was XML, this was this, and now you kind of reconstruct this data into your actual structures, right? So this is another step. So you have this additional memory copy in between those stages, which might not be that big of a deal, but as you will see in a moment, it can be quite a big deal, especially when you push a lot of data into your server. So the zero copy is all about being able to, let's say, directly reference these bytes. So you can imagine that deserialization, especially for deserialization, it's not that much of a difference. It is a bit, but it's mostly where it shines is the deserialization. So it's like casting the pointer. So the whole point, whole idea is that imagine that you receive some sort of, let's say, bytes, reference to your bytes, and then you cast it or just deserialize it into your actual structure without any additional memory copying in between. So you avoid this one additional mem copy somewhere within your first step. So you kind of receive the data, for example, on your server side, and you directly, let's say, deserialize this data into your actual structure. And this is how you can, spare some memory. So just to give you an example, so you can use, for example, a library like archive, which is probably the most popular library when it comes to the zero copy in Rust. There is also Musli, there is some sort of SERDI. Some of them full zero copy, some of these are partial zero copy. But archive is probably the most popular one. Of course, before you start using it, you should read the archive book just to understand how to apply this. But you can also implement this on your own. So here's an example of the zero copy that we did implement within our Iggy streaming. So, just playing a bit with the pointers, reading data from memory and casting to the pointer and so on. But the whole point is that once we did implement this, just to give you an example of how greatly it benefited our solution, is that here's the difference. So we did some benchmarks using our benchmarking CLI on AWS. This is the instance. So there is no zero copy, regular, copy and regular serialization and zero copy deserialization. So for the producer, we gained about 30% of the throughput. For the consumer, we've got about 100%. So we were able to go from 2 gigs to 4 gigs per second, which was full saturation of the network. It was around 25 gigabits, so it was a bit over the available AWS network for this virtual machine. So we were able to fully use the network between our virtual machines. And also this P99 latency on average dropped 2 times for the consumer side, which is still a bit above 1 millisecond because of full power, full blown, push as much data as you can. But just for changing the serialization model, we were able to gain that much, over 2 times better throughput and 2 times better latency for consuming data and almost 50% better for producing data. So this is one of the first things that we did. And here's another example. This is, I think, from my PC. 10 gigabytes per second on a bit more powerful hardware with sub-millisecond latency, 140 microseconds at this point. So we can achieve a lot with things like this. I think it took us a few weeks to implement this, but it was certainly worth it. But the next thing, and this is where things get a bit more interesting. So let's say we have this zero copy now in place. However, a lot of things will be happening whenever you build some sort of infrastructure, whenever you deal with I/O in general, because I mean, streaming server, just like database, is all about I/O. You receive some data through the network, you save some data into the disk, you read data from the disk, you send it through the network. It's all about I/O and some additional, CPU work if you do some maybe encryption, some schema changes, this sort of thing. So it's mostly it's I/O related stuff. So whenever, let's say we do I/O, let's say we save data to the disk or we read data from the network, we need to make this switch, this sort of, we can call it like a kernel user space mode to kernel space switch, which is, let's say, kind of lightweight. But once you start having like thousands or tens of thousands of this user mode to kernel mode switches at the same time, you will start seeing that your throughput goes down and your latency, they will just start becoming a bit more unpredictable, especially under heavy load. So you can, I mean, for those of you, if you are not familiar with this, yeah, it's like, imagine like I am a 3-year-old kid and I want to make a sandwich, right? And I need a knife to cut the bread, slice the bread. What I can do, I mean, if I ask my parents, they will not give me the knife to slice my bread. So I need to make like a kernel, I need to make a kernel call to my parents, slice the bread for me. They will end this bread for me, so now I can finish making the sandwich because it's safe. So from the user space, I cannot really access, let's say, the network drivers. However, there are techniques like kernel bypass where you could, let's say, access your network interface control from the user space using this kernel bypass and some specialized frameworks. But in general, all the syscalls will need to make this privilege mode switch in CPU and switch from user space to kernel space, which of course involves some, which will result in some additional time spent on doing the syscall. So from our perspective, let's take a look at this, very basic action like appending the data. So at this point, we open the file, we write to the file, append this data to the file, and of course, through the write, we close this file once this goes out of scope. So at this point, we have like at least 3 syscalls: open, write, close. Well, we can make it much better simply by, let's say, making use of something like file descriptors. So instead of like opening and closing file every time, we can just open the file descriptor for each stream or each partition or each segment, whatever we use to store it on our disk, whatever we call this file storing our messages. So when our application starts or whenever, let's say, the user makes an API call to our server saying that, OK, I want to create another stream, create this stream with this many partitions for me, we can just keep this file descriptor open for the whole lifetime of our streaming server so that we will no longer open or close this file. We'll only have write to file or read from file syscalls. So instead of 3, we'll only have 1. Right? So this is a very simple thing to do. We can just keep this file descriptors open for as long as our server is. However, of course, there is a limit. It's typically around 100K plus. So if you have a very big system and you have like 1 million partitions, it might be difficult to have descriptors open for all of them at once. So this is a bit, I don't want to say like double-edged sword, but it's easy to use, and it of course will give you like an instant benefit. But keep in mind that as your system keeps on growing, you have to remember about some limitations, depending on your hardware and your kernel. The next interesting thing. OK, so how we can deal with these syscalls, how we can improve our I/O. Have you heard or used IOUring? Do you know IOUring? Have you maybe used IOUring or more like read about it?
Haven't used like practically.
Okay.
It was practically very hard to bring. Like, so the issue is Datadog runtime on I/O.
Yes, sorry, Datadog, I think because in Datadog, Glauber Costa, who founded TorsoDB, he worked in he worked in Scala, but I think the Glomio was his runtime, and I think the Glomio was not acquired, but somehow like sponsored by Datadog, so I think it was Glomio. Glomio.
They actually have some issues because like in Rust you basically have bold-based asynchronous Just expected to close. But even if it's like more like a callback stuff,
Yes.
that's much harder actually to map this behavior to the time, and it's hard also to map basically kernel buffer to the user space. Like you need to somehow figure it out. So it brings a lot of complexity.
Yes. Yeah, I mean, you kind of need to redesign your application from the very.
Basically, it requires a complete application to be redesigned, and currently what I was doing that was practically, but I wish I can find something I could do it somewhere.
Yeah.
Because I keep it in my head all the time. Yeah, but sorry.
Yeah, that's cool. And did you use the? No. The behind you. You used what kind of framework? Do you remember? What did you use? Ah, okay.
But because there seems to be a security issue with Ionic and Wii. And I had to do it like twice already, just to not get hacked.
Yeah, I mean, but it was mostly for the Google internal purposes when you think about the security model. I mean, running IOUring in your, let's say, smartphone, probably not the best idea. But yeah, on the servers, that's fine. But yeah, that's true. So the IOUring is about, I mean, new because it's just like maybe 5 years old. So it's for Linux kernel, it's hot topic. It's very new. Yeah, but jokes aside, I mean, it's still evolving. There is still like a lot of work being done on IOUring, like new additional feature flags being added. So it's like very, I mean, there's quite a big like community around this, and it's nice to see it grow. And it includes IO for Linux. So it's like alternative for EPOL, KQ, and these sort of things. And the best part is that it's not just about the files, it's also about the network. So it gives you this one unified interface to interact with both network and storage IO, which is really good because, like I said, if you write your database engine or messaging engine or stuff like this, it's mostly about IO, network traffic and disk storage. That's pretty much all it is. And this will allow you to greatly reduce all the syscalls and all these context switches that we'll talk in a moment by doing this, I would say, simple thing in theory. So instead of, let's say, opening file one by one, or when you want to read from file and you have like 100 requests to read from 100 different files, and to do this, you need to do 100 different syscalls, you could batch all of this into the single syscall. So this can give you a lot of performance boost, and this can significantly improve your, I mean, throughput might be similar, but the latency will be much more stable because you will just simply make, for example, one call to your kernel, read from these 10 files, or write to these 10 files instead of 10 syscalls. So it will just allow you batching this multiple calls as a single one. And yeah, this is readiness-based versus completion-based. So this is like a bit of this callback model. So instead of asking, hey, is this file ready? Can I open it? Yes, open it. You simply make a call and you wait for a callback. Yeah, here is your data, right? So I read your data. Sorry, yeah. Yes.
Cancellation is more complex, but still
yes, cancellation, yeah. And if you were to ask, okay, so who's using this? So have you heard maybe about Tiger Beetle? They rolled this financial database in Zik or OLTP, which is 1,000 times faster than regular databases for transactional stuff. So if you ever looked for, let's say, Zik as a language, Tiger Beetle or Ghosty Terminal are probably these two most hyped projects in Zik. So Tiger Beetle is one of the examples. I think Redpanda, which is this Kafka alternative written in C++, using this C-star framework coming from CLDB, I think they also use IOUring internally. So yeah, this is used in real big enterprise software out there already. So the whole idea is, quite simple. So you have your user space and the kernel space, and between these two, you have this piece of shared memory. So whenever you want to read data or write data, whether this is storage or network socket, you have this submission queue where you submit, let's say, I want to write this there, and then you get this callback from the completion queue. So it's like two circular buffers or ring buffers, hence the name, IOUring, which comes from this, let's say, ring buffer as this data structure here. So this is pretty much all about IOUring, and of course, how it's implemented in C is a totally different story. And there's a bunch of flags that you can, pass to your I/O ring context depending on how you want to limit, how big the batch might be, how many, let's say, records you want to read at once, and all these things, because it will also affect your performance. Now, when it comes to Rust, there is a few frameworks. There is Tokyo I/O ring, but if you are really into performance, I wouldn't say this is the best choice. I mean, Tokyo is great for like, generic purpose backend application and stuff like this, but Tokyo I/O ring, there are better things than this. So we originally started with Mono I/O, which is actually, I think it comes from the ByteDance, which is the company behind the TikTok. It's a fully open source Apache and MIT license open source project. But recently we switched to Comp I/O, and I mean the performance-wise it's pretty much the same. So it's like maybe 1% of a difference or stuff like this. So really negligible difference. But we've just seen that I think Compio, it moves a bit more faster. Like when we ask things or when we make a pull request, they respond very quickly, sometimes within an hour. I mean, and with Mono I/O, the things just tend to be more slow, right? So last release was like a few months ago, and you make a pull request, you wait. But anyway, it's great to see that there's like more serious frameworks around I/O ring happening in Rust. I also mentioned the Glomio, which was originally made by Glauber Costa, founder of TursaDB, also written in Rust, which is this SQLite rewrite in Rust, also like a bit fancy project in the recent days. Yeah, but if you look at this example source code, so let's take a look. So what is the difference between, let's say, using this or standard library or, let's say, Tokyo and I/O, async I/O from Tokyo? So we open the file, and then let's say I want to read data from file. So I have my buffer, let's say, of capacity of 4 bytes, and then I pass this buffer to this file. So I have this read function. I pass this buffer, and then as you can see, I get this buffer back filled with this data, right? So this is pretty much all. And of course, this also supports asynchronous model. So the API looks pretty much the same, and all this, let's say, batching. So how do I write from 10 files? How do I read from 10 files at once? You just invoke this, and all this, batching, making sure that this 10 read calls to your files happen in a single batch. It's all abstracted by this runtime, right? So from your, let's say, developer perspective, you just write the code like this, and it will just work. You just pass the buffer, receive the buffer through this callback, and that's all. And this will give you quite a nice performance benefits. But then, because with I/O ring, especially in Rust, there is a bit more to it. We'll get back to this. But I wanted to also, briefly come back to this concept of getting rid of async. Because whenever we use fsync, there is some performance degradation. But the worst part about fsync is that fsync can fail, and I will elaborate on this in a moment. Have you heard about this concept, or maybe not the concept? It's more like a flag that we pass to our file called the direct I/O. Have you heard about direct I/O?
I know because I remember your presentation from Warsaw.
Oh, okay. Okay. Yeah. So I will show you the mental model in a moment, but direct I/O is all about bypassing the page kernel cache. So whenever you write data or read data, for reading data, this kernel page cache is good because you can read data from your page cache. But when you write the data, you don't write this to the disk, you write this to this page cache, and then it goes from this memory to the disk, right? Depending on your, let's say, system, which is a waste. If you want to build highly performant, database or streaming server, so all about this I/O and storage interaction, it should be like application writing data to the disk immediately, not going through some application cache and doing additional mem copy in between. So the direct I/O is a way of bypassing this kernel page cache with this DMA, which is direct memory access. This is the acronym. And this will reduce unnecessary memory copies, which again, just like with the zero copy deserialization, we reduce one mem copy within these 2 serialization steps. Same thing we can do here, like get rid of one additional memory copy that we don't need. And this will, of course, result in lower and much more predictable tail latencies because, like I mentioned a few times already, this P99 plus 39 or 49s is where our server should be as stable as possible. And of course, this will result in even better CPU and RAM utilization. So I mentioned that we want to get rid of the fsync, and we want to get rid of the fsync because it's possible that the fsync might fail. So when you make this flash or sync all, you can be like 100% certain that the data will be actually on disk and the data may not get corrupted. And if you look up this topic, this keyword fsync gate, you will find at least like a few articles regarding this matter. It's like fsync gate errors on fsync are unrecoverable. So there is a story, I think it was about the PostgreSQL originally, I think maybe about MySQL, I think originally from PostgreSQL, where there was like a critical bug, which just happened kind of nowhere in a PostgreSQL where the data would be lost in a PostgreSQL. And it happened because, let's say, you had all this fsync in place, but once the fsync reported an error to you, it was like, okay, there was some error, I didn't even notice, and I assumed the data was persisted, but data wasn't. So it was like, the whole point is that it's difficult to recover from fsync errors and even catch these fsync errors. So instead, you can use, for example, direct I/O, and it's easier if let's say your direct I/O fails with writing data to your disk, it's easier to catch these errors and handle them appropriately. But for example, retrying the writes to your disk. So this is the mental model. I took this from this blog. You can find this link here. And by the way, all these slides and all these additional links will be at the very last slide, where I will just post the QR code, so you don't need to like take photos like this. There will be just a link to the whole presentation. So the mental model is that I marked this with this orange bar. So with the direct I/O, where we have these two flags, O direct to O desync passed, it means that we go from the application memory directly to the disk storage. We omit this page cache. While with the regular model, we first would call this write, which would go from the application memory, like this first line, to the page cache, and then we will fsync, and it will go from the page cache to disk storage. So we kind of ignore this page cache part, right? So of course, when we read this data, we will not be able, let's say, to use page cache, because we have to read this from this directly. But for writing data, it's a better choice typically. And again, if you look at, for example, Redpanda, as far as I remember, they use direct I/O, and many modern database engines and metric engines, they went with direct I/O instead of just regular fsync stuff, because you get this additional performance gain here, and it's easier to deal with the potential errors when you just go for this model. So in a Rust, it's all about like passing these two flags. Of course, it's not that simple, because the fsync itself requires you to work with these blocks of 512 or 4096 bytes. So you have to work with this chunk of memory, because this is how we support. But yeah, we kind of like, implemented this, or almost finished implementing this in our project in a matter of like 1 or 2 weeks. So it's not that difficult, but again, it can give you like quite a lot in terms of your latencies and just dealing with disk and I/O in general. And one of the last parts, the context switch. So I think everyone is quite familiar with this, and it's like with our daily lives. How do we work in the most efficient way when we are not interrupted? Like when I work on a code, when I type on a keyboard and I hear someone ringing on my phone, I have to pick up the phone, I make a context switch to my smartphone, and then go back to coding, right? So I'm constantly interrupted, and I may fool myself that I work in parallel, that I can talk to a phone and write a code or stuff like this, but I'm just fooling myself. So the same would happen if we were just, if we would just use a single core CPU, right? With just a single core, single thread, we would just be constantly switching between the threads from the CPU perspective, which is a waste. So if we look at, let's say, once again, this append method, you can notice here that when we append this data to the stream, we, let's say, provide a partition ID to which we want to append this data to. And then somewhere at this point, we make this simple lock, let's say, write lock on the partition. So there might be a bit of a context switch. Of course, it's not like a full-blown process switch or thread switch. It's a rather lightweight interrupt somewhere at the user kernel level. But again, it's some sort of a context switch, right? And once again, just like with the syscalls, there might be like thousands or tens of thousands of these context switches happening every second, which will eventually degrade our performance and hit our latency as well. And well, what we can do about it? So the easiest answer is just change the runtime. I mean, when you use Tokyo, which is great runtime, and there's been a lot of great applications built with Tokyo. We built our backend that work with Tokyo. The Cloudflare built their Pingora framework, which they used to replace the Nginx in their cloud offering, right, in Rust in Tokyo. So this is great, but the main reason that it's not the best solution for IO-heavy applications or servers is that it's based on this work stealing model, where we have our CPUs, which have assigned tasks, and one CPU, let's say, sees that another CPU, let's say, is occupied heavily, and this particular CPU, this particular thread is not doing anything meaningful. It can just pick up some task from this other CPU queue and just start working on it, right? It's the way of balancing work across different cores and different threads, which is great, but I mean, once...
Consider the biggest Rust scene to allow actually
yeah.
then between threads.
Yeah, exactly.
Much more complex synchronization, which might bring much more problems.
Yeah, and this is why we need to have all these arcs, all these logs, because we have this atomic reference counts and all these logs across threads. We cannot just use RC because we have this multi-threaded, multi-core system, and we have to deal with this. So, I mean, this is fine, but once again, once you will try to push your server to its limits, you will see that with this model, it will become a bit unpredictable, because there will be a lot of these context switches between these different cores trying to pick up tasks from their own queues. And at this point, what you can do, and actually, if you were to use one of these IOU ring runtimes, it will most likely enforce you to drop this, let's say, runtime in favor of the other runtime. And the whole idea is that, OK, so what we can do, what else we can do? Well, instead of having this work stealing model in place, we can just follow or switch to this thread per core model, where the whole idea is about, it's sometimes called thread pinning. We have particular threads or threads, let's say thread pinned to the specific core. So let's say a thread 1 is pinned to the core number 1, and so on and so on. And at this point, we will not allow, let's say, thread 4 to be used by core number 1, right? So there will be like no interaction between these threads. They will be pinned to the specific cores, and they will do their job. So there will be like no context switches between the different cores and the different threads. And what it gives us is that, well, by following this concept, we could then say, so what if I will decide to pin the particular partition into this particular thread, which is then pinned to the particular core? Because I said that the partition is the way of, how we actually spread the work, is our unit of parallelization, right? So this is where we write data to or read data from. So this is a partition. So if we pin these partitions to these threads and we pin these threads to the cores, we can be then certain that whenever someone tries to write or read from this partition, there will be no context switch. It will always live on this specific core, on this specific thread. So it's much easier to like reason about potential performance when there is heavy load, because there will be like no crazy spikes, because there will be like almost zero syscalls. Of course, depending on your system, you might want to share some metadata between your threads. You might maybe want to share the list of users or their permissions or some atomic stuff like this. But in essence, all the heavy I/O, if it's kept that way, it will give you like a lot of benefits. And I mean, when it's a lightweight, when it's like a very light load to your server, you might even see that maybe work stealing works better or similar. But when it's like a very heavy load coming to your server, you will see that this is where it shines. So for example, with direct I/O, for our producer side, we've got a bit better, let's say, throughput, but we've seen P and 4 nines to be like five times better. So around like 2 or maybe 3 milliseconds compared to like 10 or 15 milliseconds when we were to compare thread per core versus work stealing model, and even better latencies and better throughput for reading the data. And this is like an example chart. It's actually coming from this mono IO runtime. So you can see how well it scales with the number of cores. So let's say for a Tokyo, there is just this amount of cores to which it scales. Then it's like pretty much the same. But for the thread per core, as you will have your job assigned to this particular course, the more cores you have, the better performance you will actually get. And the more stable your throughput and latency will be, the more cores you have. And once you start applying all these techniques like zero copy, direct I/O, I/O ring, this thread per core, some like a few days ago we were asked whether this Iggy is compute heavy, RAM heavy, CPU heavy, and the answer was it's mostly storage heavy. I mean, when you start pushing gigabytes of data to it, you will see some cores in use and some memory in use, but in most cases your cores will be the data just passing through zero copy. The memory copy is gone through the zero copy and direct I/O, so there is not much of a memory being used at all, and the data goes to the disk, and it goes through the I/O ring and all this nice batching and all these features. And of course, this is not all, because there are these other techniques like kernel bypass with these different frameworks, eBPF if you want to play very low level in the kernel and you want to build your own isolated applications that can, for example, filter network packages. You can use eBPF. So it's a lot of stuff you can dive into. And even the I/O ring itself, I mean, we've spent already a month or two on rewriting the core server part when we did the experiment last year. So yeah, this is quite some work. Yeah, but it can be done, and it's definitely worth it if you know that you have to deal with a lot of data potential in the future, and your application is it relies very heavily on I/O in general. So that's all. Like I said, this is the QR code which will redirect you to this link below it, which is just a simple website on my GitHub pages with the slides of this presentation and all these different topics like fsync, some runtime, some blocks, and the other things. So that's all. Thank you.